Hello, this is Jim Corkins. We are continuing on with accelerated motion in 2 dimensions. Okay, so if you haven't done the readings, please do so. So this first part here, this is just basically lecture tutorials, but they do help you understand accelerated motion in 2 dimensions. Okay. We're not going to do all of them. We'll do a couple of them. So here we go. In these problems, you're either going to be given something here, like 2 of these things, like the object is moving at constant speed here and here. So it's moving at constant speed and it's turning around, turning right or turning left. Okay, so and then you're supposed to draw the velocity vectors and acceleration vectors. So you need to fill everything out, given what you have. So in this case, we're given both the acceleration and velocity vectors. That means we have to fill out this, whether it's speeding up, slowing down, or turning around, or moving in a straight line, turning right or clockwise, or turning left, which would be counterclockwise. Okay, so let's try it out. Let's do this one. Here we go. So in this case, this object, which looks like it is speeding up in the negative direction. So right here, if you look at it, it's moving to the left, and there's some force accelerating it to the left or pushing it to the left. So this would be considered speeding up. So I'm going to write that here. Speed up in negative x direction. You don't need to write that part, but I am. Now, is it moving in a straight line, turning clockwise or counterclockwise? So since there is no acceleration vector perpendicular to the velocity vector, it will be moving in a straight line. Oh boy, I gotta learn how to spell. Let's try that again. Straight. There we go. Cool. In this case, let's do one that's different, very different. Right here, it says the object is moving at constant speed and it's turning clockwise. Okay, so if it's moving at a constant speed, it has no acceleration. It has no acceleration in the x direction, well, parallel to its direction of motion. So the acceleration vector in line with this is going to be equal to 0. Okay. Now, it says it's moving at constant speed, and it's also saying it's turning clockwise. So clockwise would be this direction that my mouse is moving. That means there must be an acceleration vector pushing it down at this instant. So there's going to be 2 vectors, and technically there was, this is the linear acceleration vector I indicated first. The linear acceleration vector, which is in line of the velocity vector, parallel to the velocity vector, that's 0. But the radial or tangential acceleration vector, which is technically a centripetal acceleration vector, here is pointing down. Here on these other 2 problems, you weren't given a centripetal acceleration vector or tangential vector, so I'm assuming both of those were 0 here. Okay. Let's try another one. An object slows down and it's turning clockwise. So that means it's got to have a linear acceleration vector opposite the direction it was moving. So that AL vector, linear acceleration vector, is opposite its current direction of its velocity vector. That's the definition of slowing down, is when the velocity and acceleration are in opposite directions. But for it to turn clockwise, if you're here and you're moving to the left, for you to begin turning clockwise, somebody has to start pushing you up at that instance. Okay, and again, when an acceleration vector is perpendicular to your velocity vector, that is going to turn you clockwise or counterclockwise. Okay, so let's see if you could try these other ones on your own. What is happening here? Is it speeding up, slowing down, or constant velocity? And is it in a straight line or is it turning? Okay, so try doing these on your own. Okay. Some of them will ask you to figure out the velocity vector. So over here on these ones, we're going to use blue for velocity. It says the object is speeding up. Well, if it's speeding up, then the velocity vector needs to be in line of the linear acceleration vector. So this stuff is only giving your linear acceleration vectors and velocity vectors. So we know it's got to be speeding up, so we need and it's giving you the linear acceleration vector. But there's an additional acceleration vector because it says it's got to turn counterclockwise. So clockwise, if you're moving to the right and somebody began pushing you down, you would start turning clockwise. But if you're moving to the right and somebody began pushing you up, you would start turning counterclockwise. So the centripetal acceleration vector is going to be pointing up. Okay. Ooh, this one's a good one. What happens if you have a velocity vector that is 0, but you have an acceleration vector? Okay, so that's kind of a weird one. Okay, and our choices are for this part is going to be speeding up, slowing down, or turning around. Now, when you throw a ball up in the air, and the whole point of doing this is to get you thinking about motion in 2 dimensions. When you throw a ball up in the air, it's slowing down. These are the velocity vectors, by the way, as it's moving upwards. And then when it gets right here, it comes to a stop. And then that velocity turns around and it begins to speed up in the exact speed, exact velocity vectors, but opposite direction when it's coming back down. Now, acceleration is on it the whole time. Gravity, like we learned, does not turn off. So that acceleration vector is working the whole time. I'm going to try drawing those the same size. Okay? Even when it's not moving. Okay? So whether it's moving up and slowing down, or moving down and speeding up, at that instant it comes to a stop. Acceleration is working on it, but the velocity for that instant is 0. This is called a turnaround. Okay, so this is what happens when an object turns around. Okay. It's got a momentary velocity, and I mean turning around 180 degrees. It goes from moving up to moving down. So at that instant that it's got a velocity vector, a linear velocity that's 0, but it does have a linear acceleration vector, that is when it's turning around. So in this case, when it has no velocity vector, and again you're given on this side the linear velocity and linear acceleration vectors, this is going to be a turnaround. And it'll be turning around in a straight line or 180 degrees. Okay? All right. So try these on your own, and I will, I can check them out to kind of help you out, okay, later on. And if you're given this as a tutorial, go ahead. I will post the answers to these on the following week. Now continue moving here, moving right along. we're going to do this tutorial problem. So I hope we will give you this as a tutorial for you to try. But in here, you're supposed to indicate the velocity vectors and acceleration vectors. The velocity vectors, the linear velocity vectors, and the linear acceleration vectors at each one of these points, A, B, C, D, E, and F. And it looks like you're also supposed to indicate whether it's speeding up, slowing down, or constant velocity. And so let's go ahead and see, let me get you started. So at this instant right here, when it's at A, the velocity vector is moving, which is always parallel to the direction of motion, is right there. And since it's on a downhill inclined plane, it'll be speeding up. So that means the acceleration vector is going to be in the same direction. So this will be speeding up. Okay. Now I want you to try this through the whole thing. Incidentally, it's kind of missing a G here. A G point right here. I don't know why it's missing that. So go ahead and try this on your own. So it's going to follow this track. When it hits B, it's going to be traveling in a straight line, horizontal line. At C, it's going to be kind of moving on a downhill area. Here at D, it's going to have, it's going to be at the bottom of this parabola. At E and F, it's still on the track, but at G, after F, it gets launched into the air. So at G, it's flying through the air. So go ahead and try this on your own and see how you do. Draw the velocity vectors and acceleration vectors at each one of these points. And label it whether speeding up, slowing down, or constant velocity. Go ahead and pause the video now. Okay. Let's go ahead and try this together, okay? So here we go. When we get to, so it's traveling here. It's now, the ball is sped up and it's traveled here. And now it's traveling pretty fast. When it hits B, it's definitely going to be moving to the right. But since it's on a flat part of the track, I'm assuming there's no friction, really, air friction to slow it down. So it's not going to have a linear acceleration vector. I should make sure I indicate that. And so at this instant, it's going to be traveling at a constant velocity. So I'll just label that C. All right. At point C, it is moving down and to the right at like a tangent to a circle. And since it's on an inclined plane, it's going to be speeding up as it's moving down and to the right. And on this problem, I just want you to indicate the linear velocity vectors and acceleration vectors. Don't worry about whether it's turning or not, okay? And since it's on a downhill line, it's going to be speeding up. So this will be speeding up. Okay. Let's skip D for a second because E is going to help us put D in a perspective. So E is moving up and to the right. However, since it's moving up the inclined plane, it's going to be slowing down at that instance. Okay, so its acceleration vector is opposite its direction. So it's going to be slowing down. Okay, both of these are going to help us figure out what is going on at D. So at D, it is definitely moving to the right. Again, kind of a tangent to this circle. So I'm drawing a little tangent line at this dot, and that's a velocity vector. Now, it's going from speeding up to slowing down. So at that instant, it has to have a momentary part where the acceleration vector is switching directions. It's going from down to the right to down to the left. Okay, so those two acceleration vectors, it's going to be switching directions at that instance. So weirdly enough, at that instant, it's going to have a constant velocity. Over here at F, it is moving to the right. And that acceleration vector that is here is kind of on a temporary, it's kind of like B. If this kept moving, it would be going from slowing down to speeding up. So in a way, it's kind of like B, but also D combined. So this is also a constant velocity. Now at G, something weird happens. When objects are thrown in the air, okay, their velocity is still at, that instantaneous velocity is still at a tangent to its direction of motion. However, its acceleration vector in the air is always pointed straight down towards the Earth. And that acceleration vector is actually G. Okay? So hopefully I've got you thinking about motion in 2 dimensions. Okay? And in this case, we just want to figure out the linear velocity and linear acceleration vectors. Okay? So let's go ahead. And you have a tutorial that you're supposed to do. And these 3 ones are the most important part of the tutorial. And we will do this middle one together. There is a second page to it. Okay? So let's go ahead and do this one. Now, in these problems, what you're supposed to do is you're supposed to fill out the velocity vectors in the x and y direction between 1 and 2 seconds, 2 and 3 seconds, 3 and 4 seconds. Okay? And I think that's across all of them. Now, you're also supposed to figure out the acceleration in the x, y, and total acceleration in the 1 to 3 seconds and 8 to 10 seconds on this specific one. It also indicates the time in between each dot. So this is a motion diagram. And it also tells you that in between each one of these positive marks is 1 meter. So this is a 1 meter distance. Okay? So this distance is 1 meter, and this distance would be 1 meter. Okay? So what we're going to do is we're going to begin by drawing the velocity vectors in between each one of these dots, starting from 1 second all the way to 10 seconds. Okay? So what I'm going to do, given that in between each plus mark is a 1 meter distance, let's go ahead and start off and mark up the velocity vectors as if they were directly moving from 1 second to 2 seconds. So this is the 1 second to 2 second, and I'm going to change the thickness of this ink to, let's see if that works a little. Yep, that looks a lot better. So from 1 second to 2 seconds, it goes from here to here. And then from 2 seconds to 3 seconds, it goes from here to here. And then so on and so forth. Okay, so here's what we're going to do. Now, given those arrows, which are the velocity vectors, we have to go ahead and figure out the velocity in the x direction and y direction from 1 to 2 seconds, 2 to 3 seconds, 3 to 4 seconds. Okay, so let's do that right now, and then we'll figure out the acceleration vectors later. So the velocity vector from 1 to 2 seconds was moving up. It looks like it moved up 1, 2, 3, 4. and it's moving to the right 2 places. Get that ink down to 2 as well. So these are both the components of the velocity vectors in the x direction and y direction. So from 1 to 2 seconds, it had moved 1, 2, 3, 4, so positive 4 meters over the period of 2 seconds minus 1 second. Okay, and in the x direction, it moved 2 blocks in that same period of time. So positive 2 meters over 1 second. I think I'll write that right over here. Positive 2 meters over 1 second. Okay, so we're going to answer those right here. So in the y direction, positive 4 meters over the period of 1 second, and in the x direction, positive 2 meters over the period of 1 second. All right, now let's go up and let's do this again. From 2 to 3 seconds, it goes from here to here. So that's going to be positive 3 meters over the period of 1 second. And then in the x direction, it went to the right again too, which is positive 2 meters over the period of 1 second. All right, we're going to write those in here. So we're going to put positive 2 meters over the period of 1 second and positive 3 meters over the period of 1 second. All right. Let's do the last one. Now, it moves up 2 in this case. And it's going to move to the right 2. So the blue guy is now, it looks like the blue guy is dropping over time. 2 meters over the period of 1 second. And this is going to be positive 2 meters over the period of 1 second. So it looks like it's moving at a constant velocity in the x direction, at least. But it looks like its acceleration, it does have an acceleration. If you look across all 3 of these, there's definitely acceleration there. And so let's put this information together. So in the x direction, I guess what it's asking is, what is the overall acceleration across the x direction? And intuitively, we could do this right now. It doesn't seem to be changing its velocity at all. So we would say 0 meters per second. Okay. Now, in the y direction, it does look like it's changing. It looks like it's dropping by 1 meter per second for every second, right? See the difference between these two? It's dropping by 1 meter per second for this, for in between here, and it's dropping by another one. So we could say it's dropping by negative 1 meter per second for every second. So its velocity is reducing 1 meter per second for every second. Yeah, I like the way that looks. All right. Well, let's do some calculations, which is not necessary. You don't have to do it in this case if you've already intuitively figured it out. But let's do it. All right. So the velocity from 1 to 2 seconds is, what we're going to do is this. We're going to figure out the velocity final equals velocity initial plus acceleration delta t. Okay? And I just want to prove to you that this is true. So the velocity in the end, and let's just do right here in this period of time. So from 1 to 3 seconds, okay? All right, so let's figure out this blue guy right here. So the final velocity at the 3 second mark is positive 3 meters per second. And the velocity from the 1 to 2 second mark is going to be our initial velocity, which is positive 4 meters per 1 second yeah. Now, I just don't like the way this looks. Okay, let's write it how we're supposed to properly write it. Now, the acceleration is what we're trying to solve for. And the period of time here from here to here, from this changeover, is actually only 1 second, right? If this is the initial velocity, 1 to 2 seconds, right? And this is the final velocity, there is only 1 second interchange between those two guys, right? So there was a velocity vector right in here, okay? Maybe this should say from 2 to 3 seconds. Actually, that would be confusing. But this really is only 1 second happened in between these two time frames, from the 2 seconds to 3 seconds. So I'm going to change this right here. And so this should be 9 seconds to 10 seconds. So its initial velocity at the 2 second mark is positive 4 meters per second. And its final velocity at the 3 second mark is positive 3 meters per second. So there's only 1 second change. Yep, that makes more sense now. Okay, now we need to subtract this guy onto the other side. So positive 3 meters per 1 second minus positive 4 meters per 1 second. And that's going to be equal to a times 1 second. So if you look, it's dropping by 1 meter per second, and then we divide both sides by that 1 second, and that's a. We get what we're looking at right here. Okay? Now, the acceleration vector, okay, the overall acceleration vector here is what they're asking for. Well, that is the x. If you figure it, let's assume it had an x direction component. Let's say it did, and let's say it also had a y direction component. Well, the overall velocity vector, overall acceleration vector, is what they're asking for. So this is this. So to do that, you do c squared equals a squared plus b squared, or in other words, ax squared plus ay squared, square root it. Okay. Now, again, we don't have to do this because we know the average acceleration between the 1 second mark is going to just be negative 1 meter per second, right? Or actually, it's not even going to have a direction. It's just going to be the overall average acceleration is 1 meter per second for every second. And how I know that is, in this case, the x direction is 0 meters per second squared plus a negative 1 meter per second squared that we're going to be squaring. So we're going to square those two things and then square root it. Well, this is 0 squared, which is 0. This is negative 1 squared, which is 1. The square root of 1 is 1 meter per second squared. Okay? What you find out in this one is that from 8 to 9 seconds, you're going to have this situation. It's going down, and which is -3 meters per 1 second. So it's the opposite of this. And the acceleration, and it's going to be moving to the right, +1 meter per second, right there. That looks terrible. And then finally from here to here is -4 meters per 1 second. And this red guy is going to be, again, that should be +2. And this should also be +2 meters for every 1 second. So what you find out, again, the difference between the x direction speeds is the same. So that the difference would be 0. And the difference between this -1 meters per second and the -4 meters per second is -1 meter per second over that 1 second time change. And again, what you find out, the overall average acceleration is 1 meter is 1 meter per second. Okay, so this is what you're supposed to do across all of these, and I'll correct these to make sure it makes more sense. Okay, I hope you have a good day, and that is our real quick, just basic review of accelerated motion, velocity and acceleration vectors in 2 dimensions. Okay, I hope you had a great day.